Hello everyone, my name is Glenn Desmere, bringing to you the latest advances in additive manufacturing technologies. First, I would like to acknowledge that the MIT class, Additive Manufacturing for Innovative Design and Production, has not only taught me immensely, but has inspired me to further the cause for AM by presenting on Design for AM to local SOLIDWORKS user groups. A big thank you goes out to Professor Hart and Hayden of MIT for putting this course together. The exceptional content, the quality of the instruction, the engaging assignments and case studies are second to none. Their continued involvement on social media to inform and educate the alumni is also great. Finally, I'd like to share some knowledge with friends, students, and fellow MIT CTAs and staff. The first process I want to bring to you is a metal AM process by Digital Alloys called Joule Heating. They plan on shipping printers out in early 2020, and I'd like to first start by showing you a video of the process that explains this fairly well. And as you can see, this is a very fast process. It is a DED process, directed energy deposition, and high production rates of upwards of 5 kgs per hour is achievable with this process. And wire diameters as small as 1/4 millimeter also suggest that the parts produced from this are fairly accurate, and no subsequent heat treatment is necessary after the parts are produced. As you can see here, parts that are 99.5% dense can be used. No heat treatment is needed. Any metal in wire form, as I said, and low power inputs of about 1.5 kilowatts is used. As you can see in the schematic here, current passes through this wire and jumps into the bed that completes the circuit. Joule's law suggests that the electric losses, or the heat evolved per second, is the square of the current in amps and the resistance in ohms. And the direct relationship suggests the higher the resistivity of the metal, the more efficient the process is and more heat can be generated. So this is a low energy, highly efficient process. The next metal AM process is supersonic 3D deposition by the company Speed 3D. Here the kinetic energy of fast-moving 30-micron particles moving at 600 meters per second bond together on impact. This has fairly fast production rates of about 6 kgs per hour. This is a great application for copper. Post-machining is needed to clean up the irregular surfaces. An interesting example shown here is an aluminum shell with a copper filling. Many interesting examples presented here to the right of the screen with both aluminum and copper. The trend in additive manufacturing is rapidly moving towards open source technologies. Open source hardware, open source software, and open source materials is now quite common. This open source hardware company, E3D, has a unique open source tool changer. Shown to the right bottom corner is an impressive kinematic coupling used in their quick change tooling design. It is a simple setup consisting of a plate and a block, one of which has 3 spherical projections arranged 120 degrees apart in a tripod fashion. The mating half is a clevis-style block which has 3 sets of 2 rollers each arranged in the corresponding locations 120 degrees apart. It houses a cross pin whose rotation is controlled by a thumb wheel inside the clevis. Once the plate is mated to the clevis and the cross pin is engaged, a quarter turn on the thumb wheel in the block causes the cross pin to go over a machine ramp. That in turn pulls the plate inwards to seat the projections inside the rollers, causing a precise location every time. A very nice design for quick change tooling, and is used for attachments like a microscope, an FDM head, a machining head, a CMM, a laser marker, etc. This is a very interesting printer by Nscript. It is an extremely precise printer and boasts 2-micron printing accuracy. It is a single system for multi-material and multi-processes. The printer head has 10-micron diameter dispenser and 5-axis CNC machining capability. It uses multiple heads like a FDM head, pick-and-place head, milling head, CMM head, etc. It also has bioprinting capability. Shown here on the little picture on a dime is bioprinting on an ant's head. Right above it, you can see this printer can also do small electronic sensors like this accelerometer printed on a backing. This system has a linear motor gantry that carries the print head for precise positioning. This system was launched in July aboard the SpaceX CRS-18 cargo mission, and it's on its way to the International Space Station. Here it will be used to print human cells and tissue. Shown below are also many electronic circuits printed on circuit boards. Brought to you by Optomic is this DED hybrid machine. DED as we know it is the faster but less precise process. This system has a 5-axis CNC machine combined with the DED process. It can print reactive metals like titanium. This is also a multi-material process where gradient materials can be printed. Examples are copper and bronze on steel, magnetic and non-magnetic gradient material, wear coatings like titanium carbide, etc. on materials. Another interesting display at this booth was the 3D printed sensors. The picture to the right shows a heating element printed on a stainless steel tube. In order to do this, green glass was first spun as an insulator on the stainless steel tube. A coil with gold leads was then printed over the spun-on green glass layer. This tube can heat up to 220 degrees Celsius. The next is the laser sintering process by Sintratec. Whoever imagined a laser sintering printer for less than $6,000 from the Swiss company located in the skiing capital of the world, Davos, Switzerland? Just a little side note here, Davos, Switzerland is where skiing was first invented by the British tourists who were there on vacation. Okay. This laser printer does not require an atmosphere. It has low power 2 kilowatt diode laser. It uses nylon PA12 and other open materials. One interesting use is in pharmaceuticals to make pills. Another interesting demo at this booth was metal gas coating. The laser sintered part can be held in a metal gas cloud that gets an even deposition over it. Both electrically and thermally conductive coatings on polymers are possible. The picture to the right shows a nylon PA12 sintered part with nickel plating done in a gas cloud. The Trumpf 1 kilowatt green laser TrueBuild 1000 is expected to launch in 2020. The cost of these systems are about twice the cost of an existing infrared laser. Copper and shiny reflective materials are evasive to laser sintering because of poor absorption. With the invention of the green laser, the absorption rate has increased from about 6% for an infrared laser to about 40% with a green laser. This is a huge improvement in efficiency. The wavelength of the green laser is 532 nanometers. With the green laser, copper can be printed with 99.9% density. Higher density improves the conductivity of the material. Multiple laser heads can be used to scan the entire build area. Shown below is a copper inductor with internal cooling passages printed with a green laser system. Rapidia, as the name indicates, is a faster metal AM process that has managed to eliminate the debinding stage before furnace tempering. The concept is a water-based metal paste used for AM, similar to the cartridge style and the metal filament style. The water-based paste is delivered from a canister. The picture to the top right shows the printer with two water-based canisters. One is the metal feedstock and the other canister is the support material, which is also a water-based place support. The water-based binder evaporates and the parts go directly from the printer to the sintering furnace. As you see in the picture, it is also available for 17.4pH 316L stainless steels and Inconel. The support is also an evaporative polymer support and no breaking off is needed. The process is at ambient temperature and the bed temperature is maintained at around 60 degrees Celsius. The bottom lower picture shows the sintering cycle for a copper part. The sintering process lasts about 20 hours. The process involves slow heating at 4 degrees Celsius a minute up to 380 degrees C. A dwell cycle follows for 3 hours while the part is maintained at 380 degrees C. The temperature then ramps up to 980 degrees C at a rate of 5 degrees C per minute and is maintained there for 3 more hours. The part is then cooled down gradually to ambient temperature. Additive manufacturing has opened the doors to a variety of special materials. New, better materials surface regularly at a very rapid pace. If this was not fast enough, Form Alloy has come up with a rapid alloy development apparatus, where metal alloys can be made in real time. The apparatus consists of 16 hoppers. Each hopper consists of 20 milliliters of metal powders. Powder is melted and then jetted onto the part. Precise gradient material deposition is possible with this system. The slide below shows gradient materials of copper and inconel and stellite. EBAM or electron beam additive manufacturing is widely used in the aerospace industry. One interesting fact to note is that the bed of the machine is first scanned by the same electron beam and brought up to 1100 degrees Celsius, and this takes about 45 minutes. The build chamber is also maintained at 1200 degrees Celsius. A 6 kilowatt electron beam is used and the energy absorption is about 70 to 80% and is much higher than a laser sintering process. Shown here is an RCAM electron beam melting system. The next process is a composite-based additive manufacturing process, or CBAM for short, by Impossible Objects. As shown in the steps here, carbon fiber sheets are fed into the inkjet printer. The layer shape is then printed with an inkjet printer head. PEEK or nylon powders are deposited which stick to the ink. The dry powders are then removed. The subsequent layers are printed as needed. The stack is then heated and compressed to the final stack height. Unbonded portions of the sheet and powder are removed by bead blasting. This renders the final shape of the objects.